Okay, in this lecture we are going to continue with the concept of Lorentz invariance and also extend it to a construction of space-time diagrams in order to illustrate some effects in relativity. So, what did we learn in the last lecture about Lorentz invariance? Well, we can talk about two events, event 1 and event 2, shown here on this time versus x-axis. They each have coordinates, 3 spatial coordinates and a time coordinate. And we can compute a measure between them, shown here, that delta s squared is c delta t squared minus the sum of the squares of delta x squared plus delta y squared plus delta z squared. That difference in squares turns out to be invariant from one inertial frame to the next in special relativity. Here I'd like to illustrate kind of 3 possible values, or not specific values, but regions of delta s that you may get. The first is the so-called time-like region, where delta s squared is 0. This is kind of what you naturally might expect for distance, right? In 3-dimensional space, distances are always positive, or perhaps 0, at least if you square them. So you might expect, okay, delta s squared should be 0. Well, for that to be the case, I need the sum of these squares of the spatial coordinates to be less than c delta t quantity squared between those two events. And when this is positive, it implies that there is a reference frame, an inertial frame that exists where those two events occur in one place, i.e. in the rest frame, and they're separated only by time. Therefore, they are causally connected. One event can influence the other. For example, if you have a subatomic particle that's created at the origin in its rest frame, and it decays sometime later at the same position because you're in the rest frame, then the only quantity that changed was time. The spatial coordinates did not change, and so c delta t would be non-zero. All the delta x, y's, and z's will be 0, and I'll get a positive number for delta s quantity squared. So that's a time-like region. A special case is when I get exactly 0 for delta s squared. And that can happen when the sum of these squares equals c delta t quantity squared. For example, suppose that something's moving only in the x-axis. That means that delta x has to equal c delta t. Well, that's the case when something's moving at the speed of light. So from one event to the next. And so these two events are separated by the speed of light. So that's the special case. When you go at the speed of light, you can still connect those two events, and you'll get 0 for delta s squared. But what happens if the sum of delta x, delta y, and delta z, all quantities squared, are larger than c delta t squared? Well, that's the final third case, which is referred to as a space-like separation. And that's when delta s squared is less than 0 in this formula. And what that means is no light signal can connect the two events. Events cannot influence each other. Since we've learned when we added velocities we can never exceed the speed of light, you cannot have some event occur here, where the first location is, propagate and influence what happens over this location for event 2. They're just separate. They cannot communicate to each other. In the other two cases they can. The special case you have to travel at the speed of light, but for the time-like case, some value less than the speed of light. All right, so that's just indicating kind of 3 regions for this Lorentz invariant quantity. But as I've been showing here on this diagram here, this can be a useful construct to kind of illustrate where these regions are. So let's go on to that next and talk about space-time diagrams. So this diagram of time versus space, where I just pick one of the dimensions of space, say x. In such a diagram, the motion of an object in position and time traces out a so-called world line. For example, suppose I have a particle travel at the speed of light. Then starting from the origin, it will trace out a line because time is increasing and space is increasing because it's traveling in space. And this line would correspond to the velocity equal to the speed of light. The slope of this line is the inverse of velocity. It's the inverse because we kind of showed this the wrong way, right? We have time versus x, not x versus time. X versus time means the slope would be velocity, but traditionally in these space-time diagrams we have time running vertically, so it's the inverse of velocity, 1 over v. And it's conventional in such diagrams, if something's traveling at the speed of light, we'll show it at a 45-degree angle with respect to the spatial direction. Okay. All right. What about a speed less than the speed of light, v less than c? That means the velocity is less than c. The slope is the inverse of velocity, so it's a smaller velocity. The inverse of something smaller is something larger, so it's a larger slope, right? So that's v less than c, and that's going to have an angle larger than the 45-degree angle for when we had something traveling at the speed of light. Okay? And finally, what if something just sits at rest, has velocity 0? Well, then it doesn't change in position. It's sitting at some position x, maybe x naught, and just time is increasing. So that's a vertical line. And that's the case when v equals 0. All right, so that's how you draw space-time diagrams. Let's see how a space-time diagram could be useful to understand a couple phenomena. All right? All right. So I show here just two lines. Remember that these lines represent the motion of an object in position and time. I show the one moving at the speed of light and a line for an object moving at less than the speed of light. Now remember I introduced those concepts of time-like, one of the concepts. Time-like was the case when delta s squared was greater than 0. And a frame exists where the two events occur in the same position. This region above v equals c is that time-like region for delta s squared. The special case where v is 0 is just sitting here along a fixed value of x and going up straight vertically in time. So that's the time-like regime. The light-like regime is when you're right along the diagonal there at traveling at the speed of light. And the space-like regime, that's over here to the right where you're going. You can't connect events because you would have to travel faster than the speed of light. And sorry, special relativity doesn't let you do that. You cannot go faster than the speed of light. So this is the space-like regime. This is the one where the two events you cannot communicate between the two. For the time-like, you can. All right, so that just shows you how to visualize in a space-time diagram that time-like, light-like, and space-like regions. All right, but let's use these space-time diagrams to understand another topic that we learned earlier in these lectures. For example, the Doppler effect. Okay? And I'm going to use a space-time diagram to kind of illustrate how the Doppler effect is changing the frequency between the source and the detector as something moves away or toward each other. So let's consider a rocket that leaves Earth and travels away. That would be the so-called blue world line. So maybe they started at x equals 0, t equals 0, it left Earth, it's traveling away from Earth along the x-axis, but it takes some time, so you're traveling up along this blue line. And the Earth is trying to communicate with you, so it's sending signals at a certain frequency, so many signals per second, or the waves are passing so many per second. So it's emitting these signals uniformly along its axis on the Earth's frame. And they're coming to you. Now, these signals will travel, if they're electromagnetic waves, they will travel at the speed of light to you. So those lines should be at 45 degrees, which will be less steep than the rocket, which has to be going at a slower speed. So just to point out again, the blue is the rocket's world line. This is when the rocket's going out. And as I said, the Earth is sending signals at a certain frequency, and those are the yellow lines, which are at a 45-degree angle. So since they are less steep than the blue lines for the rocket that's going less than the speed of light, they will intercept the rocket's trajectory. All right. But as we can notice, though, as the rocket travels away, the frequency of Earth signals received at the rocket is reduced. So put another way, we can look at the spacing of the signals as they're sent in the Earth's frame, but as they're received on the rocket's frame, they're getting stretched out. So there are fewer, say, on the outbound leg that the rocket receives. All right. Even those which in principle were at a time when the rocket was still going out, they haven't even reached the rocket before it reaches its turnaround point. But as the rocket travels toward the Earth, the frequency of the received signals begins to increase. So nothing's changed on the signals being emitted from the Earth. They're still traveling at 45-degree lines. They're still equally spaced in time on the Earth's reference frame. But we can see now as the rocket goes back, it's intercepting those signals more frequently. And to the rocket, it looks like the frequency of those signals has increased, whereas when it was heading out, away from the Earth, it was decreased. So head away from the object, the frequency decreases. Head toward it, it increases. And you can see that as drawn by this space-time diagram, with light being emitted on these light-like regions with a 45-degree angle, and the rocket traveling at a smaller speed, so at a steeper slope. Okay, that was the Doppler effect. Let me go back to one more conundrum in special relativity and use a space-time diagram to try to illustrate that as well. And that's the so-called twin paradox. All right, so let's take our rocket example again. And now let's suppose that these signals that Earth is sending to the rocket are signals sent maybe every year. You've got a twin, you've got a twin, two brothers or two sisters, and one stays on Earth and one travels on the rocket. They were twins, so they're the same age when the rocket leaves Earth. And by agreement, the twin that stays on Earth will send a signal every birthday, every year. Okay? So those yellow lines represent that signal. Hello, I've aged another year. And you send it out to your twin on the rocket. All right, so the conundrum is, which twin is younger when the rocket returns? We've learned about time dilation. So as the twin recedes from the Earth on the rocket, is traveling away at a speed very, well, at least comparable to the speed of light, not exceeding it, that the clock on that rocket will appear to run slow compared to the twin on Earth. So it looks like the twin on the rocket's aging less. But the twin on the rocket looks at the Earth receding the other direction and says, the astronaut will say, wait a minute, that person on the Earth, my twin, is aging less than me because time has dilated on Earth. So which one is younger when the rocket comes back? Right? How do we get out of this paradox? All right, let me just put some numbers just for example. Let's suppose the round trip for the rocket to leave Earth and come back is 11 years. So there's 11 birthday signals sent from the Earth, okay? And what we can say, though, is in the frame of the rocket for the twin that was the astronaut that traveled on the rocket, fewer years will elapse in the rocket frame in each direction because of length contraction. So now imagine you're on this blue world line and you're heading out on the rocket. All right. Actually, let's take the one on the right diagram. You're heading on the rocket. You can send signals back to your twin on Earth. So this is the opposite case. You're sending signals and they're going at a 45-degree angle because they're traveling at the speed of light, and they're going to Earth to your twin. And you send one every birthday. But you're going to send fewer signals on the outbound than you might have expected, because maybe it took 5.5 years in the Earth frame to reach your destination before turning around. But because that distance is contracted in your frame in the rocket, you're going to get there in fewer years of your own reference frame's time. So maybe you only can send 4 birthday signals before you reach the destination. Because the length was contracted, so you had in your frame, it seemed like it took less time to reach there. And the same thing on the way back. If you go at the same speed but in the opposite direction, you're going to get back to Earth, you will send 4 birthday signals. And so to you on the rocket, that's a total of 8 birthday signals you've said. You've aged 8 years in this example, which is less than 11 years. But wait a minute, how could that have been? We talked about how both thought the other's clock was running slow. Well, here's the mystery of all that explained. The time dilation symmetry is broken because the rocket must accelerate to turn around. The time dilation is working for inertial frames. An inertial frame is one where the laws of physics hold, and it has a constant velocity with respect to any other inertial frame. But if you're going to turn around, that means when you reach your destination, you're going to switch directions 180 degrees. Obviously, you have to accelerate. You've got to stop and then accelerate and switch your velocity in the opposite direction. That is not an inertial frame anymore, right? It's a non-inertial frame. You're going to feel that force, that acceleration, as you are accelerating in the opposite direction. And that resolves the ambiguity who ages less. Only one of the twins is going to feel that huge acceleration, the one that's on the rocket, not the one on the Earth. And that breaks the symmetry of who ages less. And so indeed, the astronaut on the rocket, when the rocket returns, will have aged less than the person on the Earth. Okay, that's one way to explain the twin paradox using space-time diagrams and length contraction and time dilation. All right, that ends this lecture.